Hello everyone, today we will solve a problem on the topic law of conservation of energy. Let's begin. From the top of the cliff at a height of 32 meters through a stone with a mass of 0.26 kilograms, vertically upwards. And when the stone hits the ground at the foot of the cliff, it has a velocity of 29 meters per second. Disregarding air resistance, find the initial velocity of the stone and the greatest height of the stone's ascent from the foot of the cliff. So, let's write down the questions. We have to determine the initial velocity of the stone throw and the greatest height of ascent. Let's write it as h maximal. Like in this case, we know that the rock has a height of 32 meters. The mass of the rock is 0.26 kilograms. And we know that when the rock hit the ground, its final velocity was 29 meters per second. Well, and naturally here we should also take into account the factor that air resistance is negligibly small. This will help us to solve the problem through the law of conservation of energy. What do we know about this problem? Let's show in the figure how the motion of this stone occurs. It is known that there was a throw from a height of 32 meters. This is the height of the rock, and the initial velocity is directed vertically upwards according to the problem. And it is clear that the stone, due to this throw, will rise to some height and then fall down. And at falling to the ground, it has a final velocity of 29 meters per second. We know it. How can we describe the motion of this stone? If we look at this situation from the point of view of energy, we can see that at the initial moment of time, the stone had two types of energy. That is, it was at a height of 32 meters from the ground, so it had a stock of potential energy. It had some initial speed, so it had a stock of kinetic energy. And then the energies start to pass each other, and then also when you fall down, there are transitions of these energies. But at the end, we see that the stone has only kinetic energy. And the convenience of the law of conservation will be that we can immediately connect the initial point of motion of this stone and its final point of fall, that is, neglecting the fact that it went up or down. That is, for the energy, it is not important in principle, given that its transitions, in this case, they will just help us to immediately pass from one point to another. Then we can say that the total energy at the initial moment of time was equal to the sum of two energies, its potential energy mgh and kinetic energy at the beginning mv squared in half. In the end, we can get only kinetic energy with u, and its potential energy will be 0. So we have obtained the record of the law of conservation of energy for the motion of a given stone by relating the 2 points initial and final. What can we find from here? We see that everything is known except the initial velocity. That is, from this equation, we can immediately find the initial velocity. But for this, we can make some simplification. That is, we see that the mass of the body in this case is reduced. And let's multiply all this by 2. So we get an expression 2gh plus the square of the initial velocity. That's the square of the final velocity. From here, we find the initial velocity. So we've moved the 2gh minus to the right side, and now we extract the square root. That's it. We've got the final formula. Let's put the value and calculate the initial velocity. So the final velocity of the body is equal to 29 meters per second. We square it, minus 2 times 9 whole, 800 and 200, and the height of 32 meters. Now we already have all the data in SI units, so we will not translate anything. So after calculations, we approximately get the value of 14.6 tenths of a meter per second. This will be the speed with which the stone was thrown. If we compare it with the final velocity, in principle, the answer is quite real. And therefore, further we look at the maximum height from which it began to fall down. That is, its height relative to the bottom of the rock. For this purpose, we can use different approaches, but we can consider the situation when the body began to move at a speed of 14.6 meters per second and reached its upper point of the trajectory. Here we have that velocity is 0. Then we can find the additional height to which this body has risen. Let's call it h1. And for this case, we can write the energy transition if we take the energy at this level as 0. So the starting energy of the body was equal to the kinetic energy, so it's mv squared by 2. And then the body rose to this point, to a height of h1, and the kinetic energy went to 0. But now the potential energy is not 0. It's mgh1. So this is the transition that allows you to immediately to find the height of the lift relative to the point of throwing. Oh, and we have such an expression. It remains to calculate and note that nothing here depends on the mass. That is, the mass problem was known to us, but as we see, mass does not play a role in such a movement. During the output of formulas, it is reduced. So let's calculate the value for a given height. We get 14.6 squared divided by 2 times 9.81. And we get an approximate height of 11 meters. This will be the additional height relative to the throwing point. And then what's the maximum height the body will rise from the bottom of the cliff? Which is something that you and I have to determine. And we can see from the figure that it's the sum of these two heights. H plus H1, so 32 meters plus 11 meters. And we get 43 meters. Well, in principle, the answer is also quite realistic. So this is how you can apply the law of conservation of energy in practice. You and I will see a lot of tasks ahead, where it will manifest itself in certain situations. Therefore, watch carefully how it is applied. The general logic of the application of this law will also be used in other sections of physics. So while we are studying mechanics, we should consolidate it very well. That's all for now. Goodbye, everyone.